MEM School of Engineering, Department of Mechatronics Engineering, online classes, subject Robotics and Machine Vision System, unit number 3. Myself, Saravanan, Assistant Professor, Department of Mechatronics Engineering. This is the course objective and outcomes, syllabus, textbooks and reference, and unit number 3. So last chapters we discussed about the unit number 2, that is robot interfaces. Okay, so that is type of grippers, type of tools like that we discussed. Then unit number 1 we discussed about basics of robot like that we discussed. Now we are going to define the robot mechanics. So what is mechanics? How it is work? Like that we are going to discuss in the chapter. Okay, because if we want to pick and place the robot, we need to define the position of the robot. We need to identify the where end effector will be there. Like that we need to calculate. So that is force and torque will be main concepts in the robot manipulation. That is robot mechanics. Okay, robot manipulations or robot mechanics like that we can call this. Okay, in this chapter we are going to discuss about how to represent the robot in the some matrix format, then how to calculate the position of the robot, how to calculate the torque and the force of the robot, so how to calculate the angles of links and joints like that we are going to discuss in the unit number 3. Okay, so in this unit we have two half. So first half fully based on the kinematics, that is forward kinematics and inverse kinematics. So second half based on the dynamics, that is force and torque like that we are going to analyze. Okay, so let's see the first half. That is two concepts we need to know. That is forward kinematics, another is inverse kinematics. Forward kinematics means that is angle to position. Using angle of links, we are going to find out the position of interfactor. That is what you are given. In a what we are given in a kuduthirukkom. The length of the each joint, the angle of each joint. இது ரெண்டுமே கொடுத்துருவாங்க. That is L1 and theta 1 and theta 2 like that they gave. So what need to find the position of the point. So that is x, y, z coordinate. That is the forward kinematics. Then inverse kinematics means position to angle. Okay, if we want to reach the position, so what is the angle we require? So that means what you are given, the length of the each link, the position of the some point on the robot. What you can find, the angle of each joint needed to obtain that position. So this is the inverse kinematics. That means inverse kinematics they gave the position. We need to find the theta. In forward kinematics, they gave the theta. We need to find out the XYZ positions. So this is a robot kinematics basic concept. Okay. So that is compute and end effector motion in terms of given joint motion. That is compute joint motion in terms of given end effector is inverse kinematics. So this is the forward kinematics concept. That is using theta 1 and theta 2, theta 3 value, we can calculate the position of the end effector. X, Y, Z, where it is like that. Here we have position of the end effector. So now we need to calculate the theta value, theta 1, theta 2, and theta 3. Okay, there is a robot inverse kinematics. So then what we need to know robot dynamics. So that is they are giving the input as the torque value of the each joint. That is T tau 1, tau 2, tau 3. We need to calculate the force at the end effector force. So here they gave the force value, we need to calculate the torque of the input. That is forward dynamics means compute end effector motion in terms of given joint control torques. So inverse dynamics means compute the joint control force in terms of given end effector motion. So robot control. So this is the basic concept of how to control the robot with the computer. So that is task command by the instructor, which is given to the controller. Controller given the command, that is join command to the each joins. That is how much torque is required. Okay, that is tau one and tau two, tau three, like that they are giving. So the end effector will move. So whether when the end effector is moved to the particular position, we need to find out using the sensors. So using sensors, we are getting the values and feedback to the again commander. Okay, then commander according to that, the next task will be assigned by the commander. This is a basic robot control concept. So first matrix representation of the robot. Okay, so why we go for matrix? Why we define a matrix? Because we are working in a coordinated system X, Y, Z. So we have three values. So we need to use the 3 cross 3 matrix. So only we can implement the robot in the MATLAB also. Okay, so that is a representation of a robot. Okay, so here we have an example. A point in a space. Okay, a point P in a space. So three coordinates relative to a reference frame. So that is, here we have P position is defined by the AX, CZ and BY. Okay, this is the position of the particular point in the space. Okay, this is a concept. So that is I, J, K are um, scaling vectors. So this is what how we are going to represent a point in a space. Next, represent a vector in a space. That is where we are going to define. So that is vector. That is P vector will be X, Y, Z with the W. So W is the scaling factor. So for maximum coordinate system, the scaling factor will be 1 if it is from origin. Okay, for example, if you are using the three values means P, Q, R, S means if Q with the Z values means it will not be W scale, W value will be 0. If you are with the origin, then only W value will be 1. The scale factor, it can change overall size of the vector similar to zooming function in computer graphics. When W is equal to 1, the size of components remain unchanged. When W is equal to 0, it represents a vector whose length is infinite, but T represents the direction. So it is called the directional vector. Okay, this is what representation of frame at the origin of the fixed reference frame. Okay, each unit vector is mutually perpendicular, normal orientation and approach. That is x, y, z is a normal coordinate. When we move the interfactor, it will take some vectors. That is n, o, and a. Okay, so we can represent as f is equal to like this. That is nx, yx, ax, ny, yz, ay, nz, oz, and az. Okay. So then next frame is if you are fixing the some position. Okay, if you're moving the end effector with one position to another position, so previous one is only angle rotation only, but here we are moving angle as well as moving with the end effector within a space. Okay, that means we need to add the extra row to the this one. Okay, so nx, ny, nz, that is yx, yy, z, ax, ay, az. These are the not connected with the origin point. So we need to put a scale factor for this will be 0. But P is connected with the origin. So we need to fit the scale factor. You need to remember this. Okay, so always when person is point is connected with the origin means you need to put the scale factor as the 1. Okay. So this is the representation of frame in a fixed reference frame. So next representation of rigid body. So rigid body also same represented by the same concept. This is the example. It is the concept of basic introduction of the matrix representation. Okay, if we are giving some position p value and a d value like that. If a game means it will be, we can use the matrix representation. Okay, why we go for matrix representation means if store the values in the matrix means we can calculate using the some simulator software, MATLAB like that we can easily calculate. Okay, so no need to defect. Okay, for simulators like that, so simulators also they will define the different concept only. Okay, this is the matrix representation